Okay, good morning. Welcome to the 43rd NMRG meeting. Before we all know that NMRG is a research group on network management. And we are organizing this workshop here on measurement-based network management for already the 6th time or 7th time, I'm not sure. So we started originally with looking only at net flow or IPFix-based network management, and we said for 2 years we extended to general measurement-based network management. So this is we call it a workshop. So we have 6 speakers giving insight in the current work on using network measurements for network management. And of course, this is not a conference here, so we hope that there will be a lot of interaction. We have asked the speakers to give enough time for questions and for discussions. And first of all, I want to show you this nut slide here, which you probably already know. So you can probably also find it on the IETF homepage. Well, sorry. Oh, that's the one I got from the NMRG chairs. From the NMRG head. Okay, then you gave me the wrong one. Indeed. So our agenda is, currently we have welcome speech. I mean, this 2.5 hours are not structured in any way, but we plan to have a meeting. We'll have 3 presentations before the break. Then we make a break. The duration we choose ourselves. And after that, we will have 3 other presentations, and then close at 12 o'clock. Something I forgot to tell you. So this workshop is organized by me, from the University Catholic de UCL, the Belgian UCL, not the London UCL. Suricata, who cannot be present today, and the NMRG chairs or heads or leaders, Laurent and Desandro. Desandro was around. Probably yesterday. Okay. If there are no other questions, one other thing. There is another NMRG meeting on Thursday on a different topic. So if you are interested, please join. So I would suggest that we start with first speaker, who is Lukasz Tikeli from Bologna University. So didn't have a long trip.
So, good morning, everyone. I'm Lukasz Tikeli from CESNET, or Brno University of Technology. I'm a PhD student, and I'm here to speak about our attempt to accelerate IDS systems for high-speed networks. As I already mentioned, I'm from CESNET, more specifically. So, as I already mentioned, I'm from CESNET, Czech National Research and Education Network. More specifically, I work for LibRouter Group, and our main goal is to monitor the perimeter of our network and to guard that perimeter from external or internal attacks that we can detect from monitoring these lines. So we have WASP toolset to do so from network probes, so the data acquisition from network lines, through collection, detection, storage, visualization, and remote configuration of the whole. In this presentation, I want to speak about network probes and how we collect data and how we analyze the packets. So the standard approach to monitoring probes is you have a network interface card that provides packet capture, and on those captured packets, you do some software processing on a CPU of a host server. This is the standard approach. We have an accelerated approach when the probe itself has an accelerator in FPGA, and this accelerator can somehow aid the processing of the packet. So the software performs only very specific or very advanced processing tasks, and the card can accelerate the total throughput of the system. We call this concept software-defined monitoring. The concept is here on the right, you have your processing applications, your flow exporter that exports NetFlow data in IPFix or NetFlow formats. It receives data from the card, and in the card receives packets from the line, and don't send only whole packets to the software applications, but the software applications can instruct the card to do some processing. It can either parse the packets and send only headers instead of whole packets, or we have flow cache in the hardware, so some kind of NetFlow records or aggregated records for flow can be also sent to the software instead of whole packets. And as I said, this is all controlled by the application, so it's flexible. Depending on application, you can have different requirements how this data should be pre-processed. So we measure the achievable speedups on various network monitoring tasks, and we prove for standard NetFlow we have like 5 times speedup. For application layer processing, mainly HTTP processing, we have speedup to like 3 times compared to the standard monitoring probe. But when the software needs to process every packet, we already published those results at the Infocom conference and in IEEE Transactions on Computers journal. So now the question is, can we use this system, this software-defined monitoring system, to accelerate also IDS? So not only network monitoring, but IDS. So our assumptions are that current IDS systems are not fast enough for current high-speed networks. Also that default discarding method that they use, basically blind discarding when you have an input buffer, and if the IDS is not fast enough, this buffer starts to blindly lose packets, is not good for the detections of IDS. And informed discarding can be better, can perform better. So another assumption is that usually the attacks or the threats are present in the initial packets. So usually you don't find a threat inside in the middle of a, let's say, a long video stream, but somewhere in the beginning of each network connection. So and the last assumption is the heavy-tailed character of flow sizes or network connection sizes, when you have very few heavy flows that carry majority of all the network traffic. So by dropping only the middle packets of these few heavy flows, you can get a pretty decent reduction of total network traffic that is processed by the CPU. So these are the assumptions. Using SDM, basically, to accelerate IDS, we use SDM as a pre-filter, so we don't need a flow cache in a hardware. Our application is IDS, but the system stays the same, basically. It's only a different use case, so we don't need to modify the SDM concept. We just use it for new use case. So our test setup was, we have 2 servers. Sorry. We have a traffic generator with large pcap files on an SSD drive, which we replayed but using TCP replay over a standard network interface card. These are backups collected from our network, so that it's a real traffic. It's not synthetic, it's real traffic. So the replay traffic was then delivered to our acceleration card. In that card, we have an SDM firmware, so the hardware acceleration part that forwarded packets to IDS software. And the software instructed the SDM to do the pre-filtering. We tested two IDS systems, Suricata and Snort. The testing server, just a quick stats. We've got two physical Intel processor with total of 16 cores at 2.6 gigahertz, a lot of RAM, and of course our acceleration card with SDM firmware, as I already mentioned. So with the acceleration, with the accelerator on the FPGA on the card. So for some results, first of all, it's Snort over standard libpcap interface. Now to describe the graphs, on the x-axis of both, we have a speed of the input link. So here it's from few hundred megabits per second to 2 gigabits per second. And on the higher graph, we've got buffer overflow percentage, so percentage of blindly lost packets on the input of the IDS system due to its lack of performance on given speed. And on the lower graph, we have number of detected events on that speed. The pcap was the same, so the number of detected events should be same if the detection is 100% correct. But due to, we can see from the graph that due to blind loss of packets, the number of detected events is decreasing also. So if we take a look, the green line is the IDS Snort without our acceleration. So pretty quickly, even at 250 megabits per second, the drop rate starts to rise, and therefore the detection rate drops. Using our accelerator, the drop is around 0 up till 3 times larger speed, so up till 750 megabits per second, and then starts to slowly rising as well. So the detection rate is better than without SDM. So this is what we want to achieve. Better detection rate, so the IDS need to process only packets that are interesting and therefore can detect more threats. Another similar graphs, but this time for Suricata over libpcap, we can see the same trend basically. Without SDM, the drop rate starts very quickly. With SDM, the drop rate is not so significant, and also the number of detected threat is not declining so rapidly. So we can use this IDS on even higher speeds with more precise detection rates. Now the libpcap has a problem with performance that is known, so we try to use our own driver instead of libpcap, which bypass the kernel, do zero memory copy and so on. So basically the card delivers packets directly to the application, in this case to the Suricata IDS, and the results are better. The performance is now in terms of gigabits per second, and again we can see without the acceleration, the drop rates start to increase very quickly, and the detection rate start to drop accordingly. And with SDM, with SDM, we've got better results. We've got more detected threats, more detected events, even at higher speeds. And the last graph is basically just the Suricata, the same IDS, but with a smaller rule set. For the previous test, we use all the rules that are available. For the Suricata, it's like 13,000 rules. But for this test, we reduce it only to malware detection. So the number of rules was only 1,000 or something like that. And the performance is even better, even more than 10 gigabits per second, up to 20. And we can see basically the same trend. As the drop rate is increasing, the detection rate is decreasing. And again, with SDM, we've got better performance, better detection rate. So to summarize, IDS can be accelerated using our SDM system. With reduction of packet loss, we increase the accuracy of detection. So from the other side, the SDM is applicable not only to network monitoring, but also to network security, specifically IDS acceleration. And we are preparing another Infocom paper about this acceleration. So this was just the preliminary results for this paper. So thank you for your attention.
So, any questions? Please go to the microphone. No. And present yourself and your association.
Hello, this is Jochen Kögel from Ethernet. As I understood, you drop the middle packets.
Yes.
For speed up. Can you tell how many packets do you need, and is it a fixed count of packets you need from the start of the flow, or does it vary?
We have a variable threshold on which packet we start to drop, and it's usually around like first 20 packets are analyzed, and then we start to drop, or 30 or 10, but usually it's between 20 and 30.
Okay, did you play around with this parameter, and does it impact? Okay.
If we play around, basically, after 20 or 30, the number of drop packets is basically declining, but the number of detected events is staying the same.
Okay. Okay. So, but if there's a download with a bunch of files,
yes,
and the second file is maybe with malware, then it's maybe a problem.
Yeah, maybe.
Okay.
But as I said, we try to play with the parameters and look at the graph or look at the data, look at the results, and we kind of wasn't able to see that kind of behavior in our data.
Okay. So can you tell, is it the malware detection, is it more like web traffic where you detect it, or is it typically large downloads where this effect is more predominant?
Most of the traffic on our network is HTTP or HTTPS, so it's usually web traffic.
Websites and
yeah.
Websites.
Good morning. Thanks for the presentation. Artem Gavrichenko speaking from Curator Labs. You just mentioned that a lot of traffic in the network is HTTPS. What does the solution has to do with encrypted patterns?
I don't actually know the insights of the both tested IDS, so I don't know if they do some or what kind of analysis they do. We just take the IDS and.
As per Snort, it doesn't support going into the TLS session.
But
I
think
only
that
parameters and ciphers.
I think that some threats can be detected also on the parameters of this traffic, if I'm not mistaken.
Okay. See, thanks.
I have a question from a remote participant, Ricardo Schmidt.
Okay.
He was asking how easy it is to program this system. Is it offering an API, or do you need the entire source code? Or?
Well, I mentioned Snort and Suricata. Snort has a limited support of some extensions. That's why we only tested it so far with standard libpcap interface. But for Suricata, you can implement your own plugins, basically input plugins or some different kind of plugins that can take the data for you and do some reprocessing with them. So using the plugins, using the API that is already in there, we was able to extend the system with SDM acceleration.
But let's say you have your own IDS. How hard would it be to adapt it?
Well, our SDM system has its own API. So basically, you just have to call a function to connect to SDM, and then call a function like, I don't like this flow, drop it for me, for each flow that you don't want. And that's all.
Any other question? No? Okay, thank you again. Then I would like to ask the next speaker to come. It's Abdul Kader from India. In the meanwhile, could one of you take care of the Jabber room and see whether there are questions coming up from remote participants. Will anybody do that? I tried it with my Windows PC, but it's hopeless. This looks strange. Anybody willing to go to the Jabber room? Giovanni? Thank you. We have a.
Morning. I'm Untitled Chapter, associate professor at the University of New York, and I'm going to talk about the work that we published last year in UIPS, workshop about forensics. And yes, of course. And the work is about topological analysis and visualization of network monitoring data, where we have a case study, which was the darknet traffic. The overview of the presentation. First, they will present the motivation of the work. Second, they will present some background and related work, the methodology that we applied in this work, some experimental results regarding the scanning activity and DDoS activities of the darknet, and finally conclusion, future work. So the context of the work is where we are focusing on network monitoring data, which is usually used for security, forensics, and anomaly detection. The goal is to identify malicious activities regarding the traffic patterns behind that, and the alerts that triggered these malicious activities. We focus on a specific part of this monitoring data, which is IBR, network background radiation. Basically, this data is coming from network telescopes, darknets. Usually it's noisy traffic, but important source of forensics data. We have many information that we collect through these network telescopes and darknets. The data is with a considerable volume and wide range of services and sources. The extraction of structure and compounds of this data is difficult because it's noisy and incomplete information. We have all the packets. We have not flows because it's passive. So we just receive packets from the internet. So usually the goal to study this kind of traffic is to predict and model internet malicious activities, basically large-scale scanning activities, or DDoS, denial of distributed denial of services. So to show an example of darknet, so usually it's a traffic sent to unused IP addresses. We haven't the services behind. It's just an IP address that's exposed to the internet. So there is no productive traffic, no legitimate traffic. We are in our lab. We are hosting darknet, so we silently collect all incoming packets without replying to them. So we show this example. For example, we have scanner victims of distributed botnets. So the attacker will control the victims, will start sending some packets, and this is by the which is the set of unused IP addresses. And behind this we have the sensors, it's a collector to collect all the packets, and then we are able to visualize them and analyze them. So our goal is to analyze this traffic, which is usually noisy but contains some useful information regarding large-scale scanning or large-scale DDoS activities, denial of service. So the problem that we addressed in this work was what are the compounds or the patterns of the darknet traffic, and how to filter this traffic to extract types of malicious activities, basically to extract DDoS activities and to extract scanning activities. Some work was done before, many work have been done regarding this issue, mainly to characterize internet background traffic. The first work was done by Pang et al. In 2004, where they characterized IBR traffic, basically the composition of the observed protocols and ports in this traffic. Another work was done by Moore and co-authors in 2006, where they studied the probability to observe a DOS attacks with the telescope. And Wistrow and co-authors in 2010 made another work to characterize internet background traffic over multiple darknets to extract invariant features and level of pollution of destination IP addresses. This is the first part of works regarding the characterization of IBA. More works where they focused on darknet data, basically the work of Fashka et al. 2016. And other work regarding DNS queries in 2015 by also the same authors, Fashka and all. Regarding the visualization, some work that was done. Basically, there we find some tools regarding mainly INetVis, which plots darknet data on 3D scatter plots, or some 3D visualization tools to monitor and to visualize this darknet traffic. Our work is a little bit different because we applied new technique. This technique is based on topological data analysis. It's TDA or TDA. It's a branch of mathematics where the goal is to study high-dimensional and complex data by extracting invariant geometrics feature from this data to discover relationships and patterns. So the goal is to study large-scale data, multidimensional, to extract invariant or geometric invariant. The TDA has some fundamental properties, very interesting, which are the coordinate invariance, so that does not depend on coordinate system. Analyze, which in our case is interesting because we can analyze data collected from different platforms. It is deformation invariance, so it is less sensitive to noise. Even the data is noisy, there is no problem with this data. We can apply TDA, and it is able to handle approximate data. And the third point that we obtain using TDA, the compressed version of the data, the compressed representation. So basically, we'll obtain graph. So let's take an example. So here, our example is not related to networking, but we take 3D shape, which is the rabbit of Stanford. Shape. And here we have as input data a 3D point cloud, which with many number of points. In this case, we use the filtering function, which is the eccentricity. So this function will allow us to add another dimension to the data, and on this dimension we will filter the data. It's a filtering function. I will explain later this function. And the output will be a network or a graph. Here it will be 19 vertices and 18 edges. That represents the rabbit. So this is the topological representation of this 3D shape. And the colors represents the filtering parts, the colors of the filtering function applied to the points. For example, so this blue part is the main body of the rabbit. This is the other part of the rabbit, which is part of the graph. The other part, which is the head and the feet. This is the last part of the object, which represents the bottom or the top of the ears of the rabbit. So this is the main idea. So here we have a 3D shape, and we want to apply the same technique for the network packets that we collected from the darknet. So to apply TDA in our use case, so we extracted some noisy traffic monitoring data from the darknet that we hosted in our lab, and we applied one technique from the TDA, which is the mapper algorithm. The mapper algorithm, as explained before, will allow us to obtain this topological graph, or this graph that represents the data instead of many points. So the processing steps, so we have the darknet, we have the traffic that we collected. We extract some features related to the packets, basically the source IP address, destination IP address, the ports, and the stuff. We compute the distance between the packets, We use a filter function, same as the eccentricity, for example, but we can use another one. And then we define some intervals to split this function. So we split the values of the function using many intervals. And finally, we apply the DBScan, clustering technique like DBScan, to cluster each data in each interval. And then we have this graph, which is a topological representation of our data. So this is the details of the mapper algorithm. So the input is the feature vector, which contains the feature of the packets from the darknet. Basically, in this case, we use the timestamp, the source, destination IP addresses, and the ports and the protocol, TCP or UDP. The parameters of the algorithm are the number of the intervals that we use to split the values of the filter function, and the overlapping percentage over these intervals, because we can define an overlap between the intervals, which represents something like a zoomer. When we want to zoom the graph that we will obtain later using this algorithm. In this case, we use the sample filter function, which is the identity. So from the 6 features, we have projected the same 6 features, but the technique is really flexible, so we can use another types of filtering function. And then we will put the data, our data from which are the package or the feature of the packets, use over the intervals that we defined on the filtering function. And then finally, we cluster each bit that we obtained from the interval using the DBScan clustering technique. We can use another one, but in this case, we use the DBScan technique. And finally, we create this graph where each vertex is a cluster of a bin, the cluster that we obtained using the DBScan, and the edge represents a no-empty intersection between clusters. So when we apply this technique, we obtain the graph where each vertex is a cluster obtained from the DBScan, and the link between them means that there is no empty set, no empty intersection. So we applied this technique using the DBScan. So each interval, the filtering function, and each point projected on this interval, we applied the DBScan, which requires 2 parameters. The known parameters of the DBScan clustering technique, mainly the epsilon, which is the distance between 2 points to be considered in the same cluster, and mean points represent the number of neighbors that the point should have to be considered as a cluster. And the distance function that we used in this work is the difference for timestamps attribute. For the timestamp attribute, we take the difference. And for IP destination and source addresses, we also take the difference. And for the ports and the protocols, we use the equality, which means equal or not. So it will be 0, 0, or 1. So it's this function that we use, but we can use another one. So we applied this technique over some data to darknet. We take, for example, 1,000 packets. This is the parameters that we use, and we extracted some patterns. For example, this is an example of patterns that we extracted. Here, the large green dots represent scanning activities, where we checked this manually, and we found that these are scanning activities. The red compound represents telnet and SSH access activities. The orange represents some sparse scans, and the yellow compounds represent some randomized and noisy scans. But all of these was checked manually after doing this Then we applied the technique in some data. We have 8,000 packets. This is the parameters that we use, and we are able to extract some scanning activities from the darknet. And we applied also Suricata on the same data, and we observed that we are able to detect more than Suricata. In this dataset, Suricata detects only 4 scanning activities, but we have more than 4 scanning activities using this technique. The parameters are estimated using the trial and error method. So we have to try until we find something interesting. And but when we find them, it remains stable. So we can apply them to more data sets, and we find good results. Another example of data that or activity that we extracted is regarding the DOS. So we apply this some UDP packets, DNS packets, also that are spoofed from that IP address. We use these parameters, the epsilon and the the overlap for the mapper, and we are able to find some patterns of the DOS activity, to extract them directly from the darknet and visualize them using two planes, where each plane represents the IP address, ports from the destination and the source. Regarding the platforms of the approach, so we, for example, for 1024 packets, it takes less than 1 second to analyze them using the mapper algorithm. To analyze 3 million of packets that we received for 1 day of darknet requires 11 minutes, so which is reasonable. So we can analyze a whole day with this time. We can apply this technique, for example, to know what an attacker, one specific attacker sent today. For example, we can analyze this set of 100 packets in 2 minutes, so we can know exactly what the specific attacker sent through the darknet and analyze this in a short time. But we need to increase the performance, because here we are using a single machine, so we can use more computing power, and also parallelize the tool to enhance the performance of the analysis. So, as a conclusion and future work, so in this work we presented this new technique that we are using to extract patterns from a darknet traffic. Basically, this technique used two functions. The first one is this filter function to represent one or more dimensions to filter this data and apply a number of intervals and an overlap over these intervals, and also a partial clustering using libpcap or another technique. The goal is to extract some activities, basically scanning activities or DDoS activities. And as a future work, we want to include more packet attributes and apply this to NetFlow, for example, not only the packets from the darknet, and extract more activities and also analyze their percentages. So that's it. Thank you very much for your attention. And if you have your questions, all questions are welcome. Thank you.
Hi, Stanley, UFP. So why didn't you use statistical feature extraction like principal component analysis or singular value decomposition instead of TDA?
This is the usually question we have. Yes, very interesting. The first point that we want to validate this technique. This is what we want to do in this work. We know that TDI was applied in different fields, basically for medicine, biological data, and 3D shapes. And the goal was to apply this technique and validate this, how to apply this and validate this technique on different types of data, basically data from networking. And we want to know more on this validity. How basically it's clustering. What we do here is to cluster this data, but it is more because we clustering in each interval. It's not a global clustering. So also this one for the reason that we want to validate and we obtain the good results. But I agree that we need to compare this to other techniques, like statistical techniques or SVM, or even Camins or just the libpcap, for example. This is one of the reasons why we applied the TDA to know the validity and also to compare with work.
Okay.
Another question is, are the data sets available?
The data sets most of them are collected from our darknet, which is hosted in area. To access the data, the guy is there, Jerome. We have to sign an NDA, I think.
Okay.
So
it
there
is
is a
available.
possibility, but
Okay.
there is some administrative stuff.
Okay. Thanks.
Joachim Fabini, Technische Universität Wien. Just a note, so darknet in this case is misleading. Darknet means a real region of the internet that is not supposed to be used by people like us. Dark space is a term that is used in literature correctly, and if you search about dark space, then you will find that CAIDA has a Class A network that they're doing dark space research on. And there's a lot of work in this area.
Yes, just one point here. The darknet is not the underground networks.
This is why we have the term dark space
Yes.
for this data.
Yes. So it's mainly telescope network telescope and this. Thank you.
Jochen Kögel, Ethernet. So you looked at the unused address space, the dark space. What do you think if you use other address space and apply the technique to it, like production traffic, where lots of services and clients traffic? What do you think will be the effect?
I think we can. This is one of the future work that we want to do, is to apply the same technique for, productive networks. It could be packets or even net flows to extract some patterns that will be to extract some services. But we need to find the good parameters for the algorithm, or extract also some scanning activities that targeting enterprise network. So the technique is open. We can apply this not only for the darknet, but it could be for any traffic.
I could just imagine that you find traffic patterns in production traffic which are close to the things you discover now. Yeah, like fan in, fan out. If you have a web server which is occupied by, or which is asked by many clients, and then you have something like a header scenario. Yeah. So it could be, you may end up in more false positives, I guess.
Yes, but in this case, for this specific work, we haven't the knowledge about the data. So we check it manually that could be the DOS or scanning activities. But if you apply this to real traffic, I think we need labeled data, and then we can check if and we compute this force speculative and the accuracy of the detection technique. But here we received this traffic from the darknet, so we don't know exactly what kind of traffic. It will be DOS or whatever. So yes, in this case, the validation is a little bit.
Yeah, for dark space, it's quite simple, the validation, because there will be no production traffic, so you can isolate the effects. And if you have production traffic, it's maybe just much more complicated and complex to isolate. If you want to say.
Let me check.
Yeah, just a comment.
Yes,
just curious.
This is an ongoing work. We are working on this. Yes. It would
Okay.
be good point. Thank you.
Any other questions? No? Okay, thank you very much.
Thank you.
Our last speaker before the break is Marcelo Santos, right? And if I understood correctly from Ricardo, Stinio is your supervisor. Yes, right. One question: the blue sheet is still circulating? Everybody writing their name? Okay, can you forward it to the? Yeah. Yeah, there's another one. I would like to list off and make a copy.
Okay, morning. My name is Marcelo Santos. I am a professor in Brazil. And the objective of this presentation is talking about some SDN placement challenges. So probably everybody here heard about SDN. The objective is a class about SDN, but a brief review about SDN. It's important to have in mind that we have a separation of the control plane and the data plane. In this case, we have entity called SDN controller, and it's a centralized entity. In a nutshell, SDN is a paradigm that decouples the control plane from the data plane. So we have this famous figure. In a summary, we have three layers: the network elements, the data plane, the control plane, the SDN controller, main softwares like POX, Knox, Floodlight, OpenDelight, and so on, and some SDN applications that will run over the controller. So we need to have a different view about how to treat scenarios of optimization when we think about SDN. We have now a single point of failures, and we need to think about dependability analysis in a different way. We will have overhead mainly in the SDN controller, and we need to think in a different way about planning and provisioning. And we have some problems like the flow setup time, and we need to think about where to place the SDN controller in the best way, because probably most of the people here knows that, but when you have a switch and a new flow arrives in this switch, if we don't have a specific role to this new flow, we need to consult the SDN controller, and it took some time, some additional time. So we have a lot of research questions related to this scenario. For example, what is the best placement position for each SDN controller? What is the cost of each controller? What should be the capacity of each controller? What should be the capacity of each controller? How to manage the rules and the network policies in a centralized way? How to deploy virtualized SDN controllers, and so on. So how to categorize these problems in an easy way? We propose in this presentation and probably in a draft three main placement problems about SDN. SDN controller placement problem, SDN rule placement problem, SDN hypervisor placement problem. I will start talking about SDN controller placement problem. It's a famous problem, and in summary, SDN controller placement problem, or CPP, deals with the allocation of SDN controllers in a network. It seems an easy question, but it's not. When we think about this problem, we need to decide how many controllers are required to core a network, where to place each SDN controller, and what is the controller domain. In other words, in this figure, in the right side, we can see the controller 1, and we have a lot of switches assigned to this controller, and it's a domain. So when we think about optimization and objective function, it's not polynomial problem, it's an NP-hard problem. And we have several papers about this problem. Like if we quick search for SDN controller placement problem in Scholar Google, we can find hundreds of papers about this problem. One of them, like in the first result, has more than 400 citations, and it's not a new problem. Like this paper is from 2012. So the second problem is SDN rule placement problem. it seems similar to the last problem, but it's not. When we have applications running over the controller, and when I talk that it's not one application but several applications, we need to handle the conflicts. We need to decide the best path, and it seems okay, old problem. But think about that. With SDN controller, with SDN paradigm, we can think about how to do the load balance at the same time, save energy, turn off some links, and aggregating some flows in a specific link, and everything in a real time. It's not an easy problem to solve in a real time when you have a huge network and several nodes. So we have different types of rules like access control, routing policies, traffic shaping, traffic engineer, load balancing, and we need to do everything in a real time and handle conflicts and policies. So we can think about this problem like optimization problem and use some techniques like interlinear program or some heuristics. So the last problem is SDN hypervisor placement problem. In summary, hypervisor placement solutions deals with how many hypervisor instances are needed and their position. It's very similar to the SDN controller placement problem, the first problem that I talked to 2 minutes ago. So here is an example with flow visor, or I can talk about flow N, or doesn't matter. We have a hypervisor, and the hypervisor will create abstraction for each controller in the infrastructure. Like we can have Knox and open the light and floodlight work in parallel. And it's similar to the controller placement problem, but the placement of the hypervisors demands detailed investigation because some questions arise, like where to deploy the SDN hypervisor. We need to think about hypervisor reliability and fault tolerance because we will have another layer of software, the scalable hypervisor design. And okay, I talked about some problems and I tried to define some problems related to SDN, but the question is how to solve these problems. What is the best technique to solve these problems? And the answer is there is not a best technique because it depends on the objective and the complexity of the network. How many nodes do you have, and how many resources you model? So in summary, we have two categories. Exact resolution methods that give us optimal solutions, and we have a time consume, a high time consume. Example of techniques is branch and bound, dynamic programming, and linear and integer programming. We have here a trade-off because we have exact methods to solve these problems, but they will take time. On the other hand, we have heuristics with quasi-optimal solution, reasonable computation times, like some techniques like genetic algorithms, simulated annealing, and ant colony optimization. So one normal question that arises from this presentation is, okay, I have a SDN placement problem. What is the best technique to solve this problem? That is not the best. Here is an example. We have a paper published in the III communication letter, and this paper is from 2012 and use a linear program to solve this problem. We have a model, and here we have another paper, and in this paper, dynamic controller provisioning software-defined networks, all those proposed heuristics based in simulated annealing for the same problem. But in this case, we have dynamic placement. So we need to have quick solution. We need to generate a quick solution, almost in real time, because it's a dynamic. I analyze the load in the network and decide where to put and where to create a SDN controller dynamic. The proposal is create an informational draft, identifying SDN placement problems, challenge, and solution directions. And that's it. Thank you.
Okay, so this was a presentation quite different from the others. The others were presenting solutions, while you are presenting a problem you are working on. So maybe it would be a good idea to, for questions or for what do you think? Is there anything important missing? Do you have some feedback to give? Some hints where to how to start, and so on. You think anything? How the problem has been looked at? What do you think is it a good idea to look at the problem with the three placement? Placement of the controller. How do I say it? Is from if I ask the audience, is this a good idea? Is there to target this problem? No opinion? Okay.
Anthony Lambert. Yes, from my point of view, it's quite interesting because actually, yes, this is a problem for SDN placement, but this is also a problem we find in other topics related to network management. For instance, in my company, we work in optimizing, let's say, monitoring infrastructure based on containers with hypervisor. So you have to do quite the same thing. You have to optimize the way you allocate resources and place them. And this is also a problem for, I guess, in data centers with VMs, etc. So there is a lot of problems with the same background optimization issue. So it's quite interesting to tackle such an issue in NMRG, I guess. So, yes.
Thank you.
So I'm just relaying a question from Ricardo Schmidt. He's asking, how can network measurements help in solving problems you raise in this presentation, and where the measurements should come from? So how can network measurements help on solving the problems you raise in your presentation, and where shall you measure those?
Okay, it's a good question. It depends how to treat the problem. We can treat the problem just in an analytic way. The measurement of the network can be an input in the problem, and how to measure that after the solution is generated, it depends of the problem. Each problem needs different treatment.
Thanks.
Okay. No more remarks or questions? Okay. Thank you. Okay. So we will have now a short break of around 20 minutes. So we will continue 5 to 11. So you see we have a very precise time plan. And then we will continue with the three next presentations. You will notice that the next three presentations are from industry, from companies and institutions, while the first three were from universities. So let's see what will come up interesting. Thank you. See you in 20 minutes. So welcome back to the second half of the workshop. Thanks again to Giovanni, who is taking care of the Java room. So let's start. Our next speaker. Our next speaker is Marco Davids from SIDN. And please go on.
Okay, we're all seated. Can everyone hear me? Everyone in the back too? Okay, hi. Okay, better like this? Okay. Hi everyone, everyone seated? Hey, my name is Marco Davids and I work for SIDN Labs, and we are the R&D team of the Dutch registry. So the registry running the country code top level domain. And I may be representing the industry, as Ramin said so nicely, but we are a not-profit organization, just to make things clear. And today I would like to talk briefly with you about our SPIN project. The SPIN project stands for Security and Privacy in the Internet of Things. It's a project we started recently at SIDN Labs, and it's about the Internet of Things. Now, I could argue with you about what the definition is of the Internet of Things. We've been struggling with that internally quite a while. There's a great definition of the IEEE organization. It is only 86 pages long, so you can have a look at that if you like. But I like the approach of RFC 7452. But whatever the definition is of the Internet of Things, we all agree that there will be plenty of it. There is a lot of IoT coming towards us, both in our homes as well in the enterprises. There are many research activities trying to estimate the growth. Here is one made by Gartner. The figures may differ, but everyone agrees there's going to be a lot of IoT. And with that, we will also see quite a number of problems, because all these devices entering our networks, many of them have their limitations. Like, for example, they are cheap, manufactured cheap with poor security. They have standard passwords, hard-coded passwords, telnet ports being open. Sometimes you can bypass security by just going to a direct link. So in general, there is this agreement that it's a bit of a mess and also a security nightmare. And we have also seen evidence of this. This is the famous Mirai botnet that you may have heard of, last year targeted against Dyn. We were particularly worried about this because Dyn is a DNS provider, and we also run a DNS infrastructure for .nl. And this attack brought many important services down, such as PayPal, Spotify, Netflix, you name it. And since we also run this a DNS infrastructure for .nl, this particularly triggered us. So we came together, we had this little brainstorm session, and we thought, like, what could be the solution to this problem? Should manufacturers deliver better products, or should we have legislation or international policies, or maybe even certification programs for devices? Or should we make the user more aware? Should security become a feature that sells, that there is a market demand for security? Or should we empower the users to give the user tools to be aware of the things that are happening in his home network, and give him control of what he can do within that home network? So yeah, we came to the conclusion that there is no silver bullet. Actually, we have to do all of these things to solve this problem. But for this SPIN project, we decided to focus on the empowerment of home users. We particularly targeted the home users because we believe that in the enterprise world, there's already a lot of things happening with intrusion detection systems and stuff like that. But if you look at the home user with his router, all a CPE device or a home router basically has is a simple manner of defining some firewalls. So that's how the SPIN project was born. SPIN is a research project from our labs team, and it attempts to research the user empowerment part. And that means that with our SPIN box or SPIN system or SPIN device, we hope to detect anomalies in the home network. Just to give you an example, it's not normal if your refrigerator starts sending out millions of emails all over the world. That's not typical behavior for a refrigerator. And it's also not normal if your IP camera starts scanning port 22 all over the world. That's unusual. Then what we would also like if once these anomalies are detected, that they are automatically blocked. So suspicious traffic from and to Internet of Things devices, we hope to automatically block them. And we also want to inform an average user about that. I mean, not every user is tech savvy like you are. There are many users who have very limited knowledge about how these things work. We want to inform them and also give them the ability to define some sort of security preferences for this network. So these are the research goals for this project. Our main motivation for starting this project, because it's a little bit out of our league perhaps, is we want to protect the infrastructure of operators, of DNS operators and other operators. In particular, of course, our own infrastructure. We have a direct benefit if this problem gets tackled in one way or another. But we also have this good of the internet mentality, so we would also like to give users more control over their in-home Internet of Things network. And by doing these things, we hope to preserve the trust in the internet, and that's more or less an indirect goal that will benefit us all and also ourselves. We decided to choose for what we call a user-centric approach. That means we would like to allow users to easily deploy a solution. And I'll get back to that later. We want to protect the user's privacy by keeping things local as much as possible. What I mean by that is we do not want to connect to any cloud servers to transfer all the behavior that is going on within the network, because we believe that is a privacy infringement. So we want to do as much as processing on the box itself as possible. And again, as I said earlier, we would like to allow the users, an average user, not the tech-savvy ones, to configure the system according to certain security preferences. And what we are also thinking about is to initiate some sort of collaborative initiative to work together with a group of maybe security related people to define perhaps certain security profiles. Think of a security profile that matches a smart TV, for example. A smart TV has a certain behavior, and it would be odd if a smart TV would be sending out these emails. So maybe we can define templates that a user can load into the SPIN device for specific devices. Maybe in an automated way, maybe in a manual way, I'm not sure. But the collaborative attempt is also part of this project. Here is a brief overview of the SPIN concept. It's hard to see, I suppose, but what this figure represents is a piece of hardware, a device that you install in your home network. It has incoming traffic, it has outgoing traffic, and it has a number of modules. The three main components of this thing are the three modules on the left. A module to visualize traffic, to let the user, to make the user aware of what's happening in the network, and also that there is a control panel there that allows the user to configure certain settings. There is a module that is supposed to monitor devices for odd behavior, and there is a module to control traffic, basically firewall. What this figure also shows is these groups of people on the left and the right. These are the communities feeding the system with knowledge about certain devices, like, for example, your refrigerator or your television or what have you. And again, as I said, the processing is done locally, so the device is not sending behavior of the user to a cloud service of any kind. It's processed locally, and hopefully we will manage to make this largely automated. Of course, this is a provocative thing. I'm aware of that. It's tricky to have a device have things blocking automatically, but maybe if the profiles are mature enough, we can achieve this goal as well. Yeah. At the moment, the Spin project is both a concept and running code. We decided to start writing running code from the start. So we have at the moment a prototype running. It's based on OpenWRT. And it is also currently bundled with our ValleyBox device. That is an earlier project of SIDN Labs. It is this piece of hardware on the left. It's a GeoINet, small, cheap, kind of home router device. And with the ValleyBox project, we implemented a validating resolver on that thing with trust anchor management, etc. And we took that project to enable Spin on it. So we have enhanced the ValleyBox software with Spin functionality. And one of our architectural principles is to focus on IoT devices with what we call a predictable behavior. So we clearly distinguish between a home computer, a PC, or a laptop, for example, or a tablet, because the behavior of such a device is pretty unpredictable. I mean, my behavior at my laptop is totally different from the one of my wife, for example. I do weird stuff. She just visits nice websites. But there is also a privacy issue involved there, because if I would be the manager of the Spin device in my home, I wouldn't even want to know what my wife is doing. So we left that out of the equation. We are focusing on IoT devices. Because IoT devices, a regular IoT device, at least the ones as we envision them, they have a predictable behavior. Like, for example, the refrigerator again, it may visit the manufacturer's site, maybe for a firmware update or something. But it may also visit the grocery store to order something if it noticed that you're out of milk, I don't know. But that's about it. It's not going to scan the entire internet in port 22 or do all kinds of other stuff. So we envision that we can define templates for these particular devices. And that's why we focus on that. So as you can see, the computer traffic is directly forwarded to the internet, and you can have your Internet of Things network or Internet of Things devices let their traffic pass through the Spin box. Here is a picture of an early prototype of the visualizer. It looks a bit simple, but what it does is, in the center is the IoT device. In this case, it's a Samsung Smart TV of one of my colleagues. And as you can see, it already makes a lot of connections if you turn it on to the internet. And in the very first prototype, these were IP addresses. So it showed the IP addresses it was connecting to. Of course, that's not very useful for the average user. So we build a kernel module in the Spin box that monitors DNS queries. And when it can correlate a DNS query to one of the IP addresses it connects to, then it shows the name rather than the IP address. And we noticed, for example, that this smart TV was connecting to Facebook. Now, my colleague has nothing against Facebook, but he didn't configure a Facebook account on that smart TV. So he was surprised to see that his smart TV was connecting to Facebook. The next thing you can do is you can click on the balloon showing Facebook, and you can tell the Spin device to block traffic to Facebook. That's also currently working in the current firmware. Now, we have this little IoT lab within SIDN. We're testing various devices, smart speakers, Amazon Echo, for example. And we have noticed that if you start blocking too enthusiastically, then, of course, at some point in time, the device will stop working. So that's why we are thinking of building up this community effort of, templates that you can load that belong to a certain device that you can load safely and let the device do clever things without breaking things. But anyway, this is the current situation. Speaking of current status, as I said, we have this running prototype on our ValleyBox OpenWRT platform. We started with a focus on privacy. We hope to extend that to security-related things. Like we are hoping to scan devices within the network, for example, to see if they have open ports or whatever. Our philosophy was to design a vertical slice that's kind of a narrow kind of functionality that works top to bottom. And once you extend that functionality, it becomes broader. So we add more modules as time progresses. We have this visualization module. We have this blocking module. But again, it's still all manual. And we are now working on more automation, being able to detect malicious traffic within the network, anomalies, etc. The software is free, so you can have a look at how we progressed at our GitHub site. If you happen to have the same hardware that we use, then also install firmware images straight from the Valibox website. So feel free to have a look at that, but remember it's all beta, it's all research, so don't expect any guarantees from us. The vision for the further future is it would be great if we would get the SPIN concept and maybe even the SPIN software deployed into regular home devices. We are aware of some similar initiatives, so apparently, the industry has picked this up as well. But this is all proprietary stuff, and it is cloud-based mostly. And we hope to come up with some kind of an open standard that vendors might ultimately implement in their home routers. For example, we have it running on the Turret router, which is a great thing built by the colleagues of NixCZ. And our SPIN software is running on that router. We foresee also some standardization work in regard to this. We foresee that, for example, there should be interoperability amongst Internet of Things devices. I can imagine that if you plug in an Internet of Things device in your network, it identifies itself in a secure manner to maybe the router, so that the router can download certain templates belonging to that device. So we foresee standardization work in that area concerning protocols, data formats, and APIs. For the near future, we are working on refinements and improvements of the SPIN software. We also have one huge research question, and that is how to protect the protector, how to make the SPIN device safe itself. It's also challenging. Again, we hope to initiate this collaboration effort, a platform for sharing device information in a uniform, standardized way. That's interesting. I came across a draft that seems to touch this matter. It's the draft IETF Ops AWG MUD that more or less resembles the things we're thinking of. So that's interesting that there is already some ongoing work happening in that area as well. And hopefully, ultimately, I can tell my TV to only go to Netflix and not nowhere else, not go to Facebook in my case. If you are interested in collaboration, please feel free, contact me. I'm here all week. We have also written a tech paper about this. It's a lot more elaborate than what I can share in 15 minutes. You can find it on this URL, so have a read. If you want to know more, or if you want to discuss this with me, you know where to find it. And that's it. Thank you.
Okay, questions. Just a remark, the slides will be soon online for those people who are interested in the URL, for example. Okay,
Dan Romashkano, unaffiliated. You mentioned standardization, and I just wanted to point you, maybe you are familiar already, but there is a working group called SECM about security automation and continuous monitoring. Actually does something like creating an architecture and a data model for profiling the security pattern or normal behavior of your network, and kind of pointing out the exceptions. So that would be something that you would like to look at, and at least as a starting point.
Absolutely, excellent feedback. Thank you. I will look into that.
Tim Carey at Nokia. I will say that this is actually great stuff, because in certain organizations like the Broadband Forum, we actually were developing a new protocol. You talked about is there standardization going on? There's a new protocol called the Universal Services Platform, which actually has a controller and agent, and it's focused in the home area network. So your effect, your devices actually would be a controller there, and they've got the discovery, authentication, all that stuff already taken care of. The other thing is that an LMAP, right? If you look at a diagnostic piece within these devices, whether it's an IoT device or in the router, that's also a possibility because we're really looking at a diagnostic task. But this is actually great work because we are very interested, particularly out of the broadband forum, in how do we troubleshoot, diagnose, and react towards the events that happen within the home. And so we're thinking along those same type of lines. So I'll be interested in talking to you afterwards and maybe seeing what we can do because this is good work.
That's great confirmation that we're on the right track in one way or another. Thank you. That's it. No more questions.
I had a question, but I forgot it. It was, give me 1 second. Maybe I will remember later. Okay, thank you again. That was very interesting. Oh, by the way, is there anybody here working maybe for manufacturer of such devices? Nobody here? That would be great to hear feedback on this idea. Okay. So our next speaker is Jochen Kügel from Ethernet. And okay, and Sebastian. Sorry. So we have 2 speakers.
Okay, so this is actually from industry. We are from Ethernet, and this is about indirect passive measurement of network characteristics in the Automon project. I will give the introduction and the vision and use cases of the Automon project, how this work is linked, and Sebastian will then talk about the indirect passive measurement. He mainly did the work in this area. So the plan is first to introduce the Automon project, the vision of measurement control there, and then dive into the problem statement of unobserved paths, where we have this approach for passive sampled measurement, which is currently work in progress, but we want to present it and maybe you get some idea, or you can tell us some pointers or give your feedback on it. We'll present some first results and with conclusion and outlook. So briefly, Automon project. The project goal is automated performance monitoring. So bringing more automation in the whole performance measurement and monitoring things. It's funded by the German government, and it's a program for small and medium enterprises. So SMEs, we are one of those. Time frame is 2016 until 2019. So we are in the beginning, and you can visit the website if you like. In order to get a better impression of the project, it's maybe makes sense to tell you about the partners. We have some application partners which are directly interested in the results we have, and they provide problem statements, use cases, scenarios. They have some labs. We can get the network data. These are Deutsche Bahn and IBM. And we have research partners, which is university and 2 enterprises. So Deutsche Bahn, it's Systel. It's a service provider for the German railway and also for global logistics. So everything which is connected to Deutsche Bahn. Then there's IBM, and it's IBM Multi-Network WAN services. They provide connectivity and services to airlines and global enterprises. It formerly belonged to Lufthansa Systems. Now it's basically, they use the platform and sell it via IBM, and they're now part of IBM. Then there's Technical University of Munich, the chair of network architectures and services from Professor Karle. Then for the small medium enterprises, it's us, it's ISONET. We have a network monitoring solution called ISR-Flow. It's mainly flow-based, but we do all things like large-scale enterprise network measurement and monitoring. And we also have a second department which does network consulting. So we're a very knowledge-based company in Munich, and we have a couple of large customers in Germany. Then there's another small company. It's Sandstorm Media. It's from Dresden, and they have something which is for data exploration, a tool which is called XFly. You can get it for Jira. Just recently as plugin, and they're contributor to the NEOS content management system. So they're really user-centric and UI-based. So it's quite a good mix in the consortium to have basically the two companies here for research, companies for application. We have quite a good work together and ideas. Okay, so what is the idea of the Automon project? Why do we think we need more automation? Today's challenges in network monitoring is that the network infrastructure is business critical, but it becomes more and more business critical, especially in enterprise networks. So if there's something broken, then production stops, yeah, or whatever. You cannot do your bank transfers, whatever. And at the same time, you have fewer and fewer people operating increasingly large networks. So manpower is declining, but you still have to be able to operate large networks. Additionally, you have high dynamics in networks due to softwareization, like SDN and all automation things. So the network becomes a more and more moving part. So this makes the automation of network monitoring mandatory, because the network moves and is automated, and so has the network monitoring to be as well. Of course, there's always the discussion, is it only monitoring, so does it stop at monitoring, or is it also reconfiguration of the network? That's also a continuous discussion with our application partners and with our customers in terms of liability. What if the automation breaks the network because your monitoring system says you have to change the network? Who's liable for that? This is just something which is in discussion. The vision of Automon is basically, well, you have some users and you have a data center in between. You have wide area network, and there might be interfering traffic, and you want to detect this traffic. So this is something which happens quite often in network operations. And what you do today is you have basically the network monitoring system, which collects the data, metering and export via IPFix or other mechanisms. And then you have a monitoring system here that you have to configure initially. You have also configure the router. Then you have to manually, interactively do the problem analysis. You do the drill down through several charts and diagrams, and in the end, you have an analyst report compilation. But this is typically done manual by the operations people. And then you link it with other tickets from the ticket data, and in the end, you have the management report. Your management tells you, well, this application broke down. What's the reason for it? You have to do lots of these things manually today in order to end up with a solution and a report. And in Automon, we want to automate the whole process. So we want to start a configuration of the network infrastructure and the network monitoring system. We do the problem analysis mostly automatically, and we can then do adaptive adjustments in case we need more fine-grained data from the system or from the routers. We are aiming towards a traceability and visualization so that you already get the result presented that you would otherwise do manually by drill downs. Linking with other data, if you get some insights there, there's basically the expert in the loop, the user, which can feed back to this one. And in the end, we have the automated generation of the management report. So this is the vision of the complete project. And we have now one specific case where we get a little bit more down to earth. The problem of unobserved paths. So this problem just came up in a meeting. We discussed some approach, and this is, for example, the scenario Deutsche Bahn. You have a van which is monitored. You have active measurements there, like CISO, ATCO, IPSLA to all locations. You continuously know what's going on there. But then you have the access network out there, and you don't know what's going on there. And if an application breaks or is slow, and the issue is somewhere over there, you may not know. So you have unobserved path, and you even don't know at any time which client is over there. And these could be, for example, high queuing delays, access network issues, high processing delay in the routers because they are mostly software-based here, or there can be any error that you cannot imagine. Yeah, so this is why we measure. We measure because we want to see the performance of the network, and that's why we think it's important to look into these unobserved paths. And the idea we got is we could sample packets in here, and we can do some timestamp analysis from the traffic that goes into this direction. This came up when we discussed the paper on SKU-based sibling detection based on TCP timestamps from Technical University Munich. So this is basically the TCP and flow timestamp analysis that we are currently looking at. Of course, it's not possible. It's a coarse-grained approach, so it's not possible to get really the jitter packet by packet. But generally, we are interested in worsening network conditions. So if in general the network conditions become worse, then they impact the interactive business applications. For example, these are some charts from round-trip times where the round-trip time suddenly increases from 300 to 400, or we have peaks of even 700 millisecond round-trip time. So these are effects observed in an enterprise network, and you want to know if there are such effects that impact your application. So it's just, we just want to know, is the network becoming worse? Because then we can say, well, it's in a bad condition. Then we trigger further automated investigation via Automon mechanisms. And if it's in a good condition and application users complain, then you know nothing changed and you're still safe and the network is still the same as before due to measurement. And now the research question is, how well can we passively measure jitter and delay increases and those large-scale delay variations? And that's our current work. And I will hand over to Sebastian to explain this.
Thank you, Jochen. Okay, so in the following, I'm going to present our technical approach a little bit more in detail, and in particular, how do we do this passive monitoring in principle? Well, as Jochen indicated before, we rely on timestamp information. Now, what timestamps are typically available to us? As you can see here in this simplified scenario, we assume that we have hosts which communicate with some servers, and we have some TCP communication, including the TCP segments with a timestamp option set, which is usual for most current Linux host implementations and also most current Windows operating systems. So this is the first timing information we get, the time of the host system or the server. The second time information which we collect is the time at which we do packet sampling on the router. So what we do is we take every 100th of thousands packets and we take a snapshot of its payload, including the timestamp option. We also know what time was it from the perspective of the router when we took the sample. And then we try to establish a relation between these two timestamps. And based on this equation, which I'm going to show you on the next slide, we are attempting to detect delay variations. Of course, with this approach, there are some challenges. In particular, how accurate are the clocks in the router and in the host? How much TCP traffic with TCP timestamps option is actually available in the network? And how many samples do we need in order to get some valid measurements? Well, our basic assumption is like this. In the first step, we assume that clocks, they don't jump, they don't drift, so we live in a perfect world, and we can establish a linear relation between the timestamps of the host and the timestamp of the router. So we assume that we can take the TCP timestamp of our measurement sample and relate it to the packet timestamp sample in the router, and do this for several samples, and we will end up with some sort of a linear equation like the timestamp of TCP equals some slope m multiplied with the packet sampling timestamp plus some offset. Now, of course, there are two unknown variables in here, the slope and the offset, and I'm going to show you in the following how we tried to gain some insight into the correct values of these. For the slope, we did a very simple approach. We did an offline analysis, so we collected packet samples of our TCP flows, and in a second step, we analyzed how much is the delta of the TCP timestamps compared to the delta of the packet sampling timestamps. And we did this for each consecutive packet sample which we got. Now, of course, we are aware that there is probably a lot of noise on the packet sampling timestamp because we will measure delay, jitter, processing delay, and that. But still, our results showed there are distinct peaks for different values of M. And we got two insights. First of all, well, even with this noise, there is a way to guess the most likely slope, at least if your sample size is large enough. And second of all, there are two typical peaks. For Windows host, this peak is at 0.25, and for Linux host, it's at 1. But in the end, this means that we have to do this slope estimation, for every flow which we observe. Now, with this knowledge, we still miss the second variable, the offset b, and we try to estimate the value for it like this. First of all, we start with our initial packet sample. We now know the slope m, and we know the observed packet sampling timestamp and the TCP timestamp, and we just calculate an initial value for b, or the offset. And for every consecutive sample, we use this b value and try to calculate what time would we expect to at what time we expect to observe a particular TCP timestamp. Now, if we should be wrong with our estimation, for instance, we see that the measured timestamp for a particular TCP's timestamp actually arrived much sooner than predicted. This means that the sample which we currently process probably expected less processing or queuing delay or whatever. And this means that our current estimation for B was wrong, and we have to adjust it and take the new minimum maximum. And by iterating over all samples of a TCP flow, we will eventually get the offset which reflects the minimum processing and packet delay. So now we have suitable values for the slope and the offset, and we can start to actually calculate the delay variation. And I'm going to show you in the two last slides some preliminary results. As I said before, we did offline processing, but we did it with real traffic in our intranet. So we have local area network as well as wide area network in this. However, we don't have any well-known test traffic. We don't have any well-known delay or jitter. But still, we see some interesting results, even if we don't have any, well, let's say, lab setup conditions. In the first picture, you see a flow which has a duration of about 2 or 3 minutes. And as we can see here, the calculated delay variation is typically around 1 to 5 milliseconds. And at the first glance, there are no outliers at all. And so we assume that this was local area network traffic, that our measurement accuracy is probably around somewhere between 1 and 5 milliseconds. So in the worst case, 5 milliseconds. So not too bad. Last result slide. This is a flow which was measured for a IP address destination in the internet. So this is wide area network traffic, and it was quite a long-lived flow. We see here that this is going on for 12 hours, and we see here an interesting sawtooth pattern. We don't see this sawtooth pattern for every flow which we observed in our measurements, but only for some, and hence we assume that this is probably an issue with the clock on the host, which drifts and eventually gets corrected again. I don't know, maybe NTP or something like that. But which means in the end that for our approach, we will have to consider clock drift and other clock effects in the future. Now, how does this fit into the big picture? What does delay variation mean? Does this boil down to a MOS value? No. Can you make any statements about voice quality with just this value? No again. It's useful for us as a first indicator for anomalies in the network. So if we see that the delay variation is typically around 5 milliseconds, and then at some point we see some weird peaks, which can be done with this passive approach, this is an input for Automon control loop to trigger additional and more fine-grained monitoring, as we intend to do in the Automon project. Okay, so let me jump to the last slide. So as we have seen, the passive monitoring of delay variations using TCP timestamps seems feasible, at least for the scenarios which we had a look at. And we assume the assumption that the clock drift is negligible didn't hold. However, the timestamp accuracy of routers has improved a lot. So actually now it's feasible to do measurements in the order of magnitude of, well, small number of milliseconds. Our future work includes that we set up a test lab where we have delay, jitter, and everything under control so that we can have a further look at how accurate we actually can measure. And second of all, that we do more measurements in the network of our application partner, in particular Deutsche Bahn Systems. Last but not least, we also want to redesign our approach so that we can migrate from offline towards online processing and also take into account the clock drift and stuff like that. Okay, this concludes our talk. Thank you for your attention, and we are happy to take your questions.
Jochen Fabini. Is it IP version 4 or IP version 6?
Well, at the moment, our router is capable of IPv4 and IPv6. I think for the measurements we did so far, we relied on IPv4.
Okay, just because for conveying timestamps, many people have similar problems, and there's now a draft in the IETF editor's queue. It's about IP version 6 performance and diagnostic metrics destination options. So they have a destination option extension header field in IP version 6 where they exactly put this timestamp, sequence numbers, and so on the track for conveying the...
This is quite interesting because at the moment we're limited to TCP traffic and only TCP traffic with the timestamp option set, and this is some fraction of the overall traffic, and with the IP protocol this would be much more interesting because the visibility would increase, at least for IPv6 traffic.
This is why I mentioned it. So you can go the standardized way.
Thanks for your comment.
Wes Hardiker, University of Southern California. Fantastic work, so thanks for bringing it. It's interesting to look at the data. Have you considered the effects of mobile devices as they change between, say, different access points and things like that, or distance from the access point, which might cause a sawtooth pattern or other strange, artifacts as the world goes more and more mobile? I don't necessarily mean cell phone network, but even access points for wireless networks like the IETF.
We should see some mobile devices in our internet because, well, of course, everybody of us has some smartphone. But I didn't have a look at the mobile so far. So the results which we had a look at were just fixed hooks. Okay. So these effects are probably quite interesting, but we didn't have to look at it yet. And I think also, I don't know, Jochen, do you have a comment about our unlimited bundle or application partner? I think those are the most buyers.
Yeah, well, I think we have to ask. Typically, the wireless devices in enterprise, they live in separate subnets, so I think you can easily distinguish them, and then I think it's interesting to look into this.
Yeah, I'd love to see a graph of it. That's what drove my curiosity. Second real quick question is, have you looked into turning any of these data sets into sort of notifications and looked at issues with too many false positives and things like that with trying to actually detect real problems using the data that you come up with? I mean, you've come up with a whole bunch of interesting data sets, but you haven't talked about how to turn them into something useful in terms of management.
Well, this is really preliminary work, and the results you saw were Friday, so we're just at the beginning. So no, we haven't done that yet. But again, interesting.
Keep going.
All right, relay another question here. So Ricardo Schmidt, Molly, he's asking if you plan a standard draft or even RFC on this work, and if so, which working group would you choose?
We have not thought about it yet, but if we maybe have a clearer picture of the problem and solution space, there would be a possibility. I don't know, maybe it's IP performance measurement, but let's see what it will be about. Yeah.
Okay, thank you.
Thank you again. It's interesting. Okay, our last speaker. Just a reminder to all remote participants, as you can see, you can ask questions. You can even speak by audio. Also, this seems to be a new feature. I don't know how it works. Otherwise, just write your question down to Jabber. We are following you on the chat. Giovanni is doing that.
Okay, hi everybody. My name is Thomas Green, and I started my PhD a few months ago with Orange and Telecom Paris. My talk today is going to be a bit different from what you've seen before, but I hope you will find it interesting. So my PhD thesis is on interdomain routing and security. So let's dive into it. So a bit of context first. So BGP has been there for a few decades now, so I guess most of you know how it works. To summarize, it provides kind of a opaque and complex environment. For example, you have a limited visibility of the topology. You have limited portion of information due to the best path selection, and of course you have questions of legitimacy and integrity. This means that you have still a lot of incidents and attacks ongoing, and that's why in 2017 you have still PhD thesis, including mine, on the subject. So the main idea behind this work comes from the fact that AES relationships are made by business agreements, which are negotiated a few times a year, and this also enforces the idea that the interdomain structure must be stable, at least on a large part. About the methodology, so a bit of overview of the definitions and the synoptic of the process of BGP dynamics analysis. So the first definition, a primary pass, we basically want to build a referential of a stable structure of BGP, so the internet. And so we build a referential of what we call primary path, which is the most used path for each router prefix pair. And from this, we want to interpret the flow of incoming updates messages into primary path unavailability, so to compare it to the primary path referential that we build. Since the pseudo event is a primary path unavailability period. So here is a quick overview on the synoptic of BGP dynamic analysis. So this is where we take place, and at an extent we want to, after that, be able, out of this BGP dynamic analysis, to extract and detect events and be able to mitigate them eventually. A bit more precision on what is a pseudo event. So basically, as I said, we're transforming the stream of updates into a stream of pseudo events, which basically groups updates together, messages together, following a primary path flow. So you can expect from that to see two types of pseudo events. So pseudo events that are what we call transient, which translate into events that go back, lose the primary path, and then after some path exploration phenomenon, go back onto the primary path again. So expect to see those kind of events quite often, and with a lot of with short duration. Sorry. Also, you expect to see from those kind of pseudo events to see structural pseudo events, which basically are pseudo events where you switch from your old primary path that you have in your referential to a new primary path, which can be due to a change in policy, business policies, for example. So yeah, this is the two types of events that we want to see, and we want to take a look at the temporal and topological characteristics of those events to analyze BGP dynamics. So let's take a look at the first results. So for this work, we took data from one monitor from the Right Price project on a 3-month period. So the data set is pretty relevant because it had several vantage points. But for future work, we intend to extend those monitoring points. So first, what we want to look at is the first thing we want to look at is the turnover of primary paths. So basically, it's answering the question, how stable our primary paths over long period of times. So to do that, we computed primary paths calculated on April 2016 and compared them to the primary paths that we would find on different months following this one. So you can see that primary paths are pretty stable over time. So after 1 year, you almost have still 50% of primary paths that are still the primary paths that you find 1 year later. But it is definitely decreasing over time. So you need to identify the structural changes and to incorporate them into your referential and be able to update this referential periodically to have a meaningful view of the stability. Second thing we look at is the prevalence of primary paths. So do they exist, and how stable are they? So we have this is a figure on the complementary CDF of the primary path usage for all pairs of the dataset on the 3 months period. So you can see that first IPv6 is a bit more stable than IPv4. So basically, you have a large part of primary paths that are in use for long period of time, so almost all the 3 months period. But you have also some that are pretty unstable and not used. So for IPv6, it's even more clear. Yeah. So second thing we want to look at is take a closer look on pseudo events. So this confirms the first assumption. So you can see that you have almost all pseudo events that we find are events that come back to the primary path that we calculated from the referential, and you have a few of structural pseudo events. We want on the top x-axis you can find more friendly, human-friendly units than those log scale seconds, right? You can see that for transient pseudo events, they basically have short durations, most of them, so under a minute for about 50 of IPv4. Only 12.9% are longer than 1 hour. And for IPv6, it's almost the same trend. About the structural pseudo events, you can see that they, on the contrary, have way longer duration. So only 11.5% less than 1 week for IPv4. So yeah, this again, this confirms our assumptions on the expected properties of the pseudo events. So this is a good thing. So how do we benefit from those pseudo events, and how do they help us to analyze BGP dynamics? So you can see that first you gain, with those new pseudo events objects, you gain a factor in terms of volume, again about almost 1 order of magnitude for IPv4 and IPv6, which mainly comes from the fact that, remember, the pseudo events include all updates during the path exploration following a primary path fall. It comes from the fact that you group updates together, and you can see that for a lot of transient pseudo event, at least, you have only one path that you switch on the path exploration before you go back again onto the primary path. And about most of them are at the maximum 5 paths in the path exploration, and the trends are the same for IPv4 and IPv6. The second benefit that we have from this is that it is semantically rich. So to do that, so the tables are a bit complicated to understand at first, so I'm going to explain them. So we compared BGPmon.net, which is a public service that do hijacks and any kind of event detection on BGP. So we wanted to compare our methodology and apply it on a use case to detect outages and hijacks compared to BGPmon. So you can find the reports on bgpstream.com and their public website. So first, on the outages type of events, so out of all observable events that we could see in our dataset, meaning that we have at least one update related to the prefix and that they say is impacted by the outage, we can, for most of them, detect them in the same time. So basically what we look at is, do we have a pseudo event corresponding to the starting time announced by BGPmon that translates into the pseudo event domain? So the answer is yes for most of them. And even for a non-negligible part, about 50%, we can detect in the pseudo event domain, we detect them before than they do. So we said there is a pseudo event that translates the primary pass and availability before them. And actually, out of those 236 early detected events, there is a significant detection phase about 1 hour before what they announced, for about 90% of them, I think. And only for about 1.9% of the events, we didn't find any pseudo event related to this outage. Another type of events that they report are hijacks, so just MOS hijacks, or multiple origin AS hijacks. So you just want to look at the origin AS announcing the hijack. So out of the observable events, we can say, so the table may be a bit confusing at first because we appears to be missing a large part, but actually when we manually inspected the results, it seemed that there was only due to one prefix, which was less specific prefix, which was illegitimately announced, which triggered a lot of hijack events because of all more specific announcements. So explicit legitimate means that we found when we compared to in the pseudo event domain and the primary pass referential, when we compared that, we saw that there was a primary pass for this specific event, and that for us, the hijack was not a hijack because the origin AS was the one we had calculated in the primary pass referential. And for those events, implicit legitimate means that for its prefix less legitimate, less specific, yes, sorry, we could find events implicit legitimate means that we could find an event due to a less specific prefix inside. So for us, we didn't find any primary pass. Yes, we didn't find any primary pass for those events, which means that we cannot say that this is a hijack because we don't have any primary pass to this value. Right. So to conclude on those first results, we can safely say or confirm that the entitlement is pretty stable for the most part, and that pseudo events are useful and compact objects to study BGP dynamics. We have extended work, of course, in progress for now with more data, as I said before, so more monitoring points to have a more meaningful view of the internet. And we also going to include new results, for example, to better analyze the structural events or what are their properties really, and also to be able to remove all the BGP noise, so the pseudo events that we see, for example, the transient pseudo events, to be able to remove all that noise. So, and if you have any suggestions on new interesting results that we can include, let me know. I guess that will conclude my talk. Thank you for your attention, and if you have any questions or remarks, let me know.
Questions?
Yeah, nice presentation. I just have a question, Giovanni, Italian, by the way. There are some people who use IP Anycast, which just allows you to announce the same prefix from multiple locations across the globe.
Yes.
And some people use the same autonomous system. Some people use different autonomous systems. So how that would play a role into your methodology? If you use different autonomous system numbers.
Yes, it's true. So actually, we want to refine a bit of our methodology to take into account such specific cases, because indeed we can have a lot of cases. We are really looking at the primary pass from a router and an AS. So a router belonging to an AS to a prefix. So indeed, those kind of network practice can impact, and we gonna look into that to make sure that we take them into account.
All right, thank you. Thanks. And when you see the primary effects on the figure that it had in the beginning, they kind of 50% remain stable over 1 year. Yeah,
it's after, yes. Just after.
Yes. Yeah, it's very interesting, but could you elaborate what a little bit, because I'm also curious about it. What do you think were the reasons for that, and why 50% change?
Oh, you mean on the table here?
Yeah.
So so basically, for us, it means that you have other business agreements that change providers, for example. So you're gonna get different AS paths. You have also some engineering practices that can impact the AS path, because we look really, the primary path is the entire path that we look at, not so if you have one new AS or one less AS in the AS path, you're gonna have a mismatch, of course. So we want to refine this methodology to include such specific cases and have a more precise and defined definition of the primary path.
Yes. If people do prepending, like adding the simultaneous system number, does it count as a change in the primary path?
Yes.
All right.
For now, yes. But because we think it's, it's a legitimate path. So for now, yes.
All right. Thank you.
Also questions? Okay. Well, thank you again.
So we're perfectly in time. Thank you again for all coming. So we are planning to do this workshop next year again, provided that we get a big enough time slot for the meeting. Please consider joining the NMRG mailing list. Again, a reminder that there's another NMRG meeting, not related to this one, on Thursday evening. And the agenda will be published soon by Alessandro. Okay. There's another meeting of the NMRG. Yes. Sorry? Yes. Thursday, I think 6 o'clock or something. Okay, thanks. If you have not yet written your name here on the list here, please consider. And for the speakers who have not yet sent me your slide set, please send it to me or to Lisandro or Ricardo. Thank you.